So, what we want to talk about today, we're going to finish up our Chapter 5 unit, our unit on gases. We've run across a couple of situations where people have said, well, do all gases behave like ideal gases? Under what conditions might a gas not follow the ideal gas law? What are the sort of situations where we have to be aware of this kind of difference in gas behavior? So when do we have to really think about real gases versus ideal gases? And how big of a difference is there? And what factors influence whether a substance will be a real gas or behave as a real gas or behave as an ideal gas? Much of what we're going to be talking about is sort of deviations from ideal gas behavior. Okay? Question?
So is a real gas the one that's most commonly occurs in nature?
So
That might call the real one.
what we talk about, the equation that we're going to talk about in terms of real gases are some corrections to the ideal gas law. They don't take into account everything, but they correct for two of the sort of biggest sort of problems with the ideal gas law. Two of the biggest assumptions about the ideal gas law that don't turn out to be true. Now, the ideal gas law works really well for a wide range of gases under certain conditions. Some gases, not so much, and some conditions, not so much, and that's sort of what we're going to talk about. So we've talked about this before when we talked about sort of the kinetic molecular theory. There were four important postulates of gases. Two of those postulates we talked about as being pretty big simplifications of reality. Okay? One of them was the idea that the gas particles take up next to no volume, or we assume they take up zero volume as compared to the volume that the whole gas occupies, because the particles are zipping around the container. The actual volume of the molecules, the gas particles, was insignificant compared to the volume that the gas occupied. Okay? Now, clearly that can't be true. The gas particles actually have some volume. Okay? And one of the corrections that we can put into the ideal gas law is the idea that we want to correct the volume available to the particles for the volume that the particles themselves occupy. Essentially, the volume of the container would be our V. That's the V that we've been using. And from that, we have to subtract out the volume that the individual gas molecules occupy. And that relies on how many gas particles are there, how many molecules or moles of particles, and what is the volume of the particles themselves per mole. And so this value B is used in as a correction factor that is roughly proportional to the volume of the gas particles. Larger particles, particles with a bigger volume, molecules of a gas with a bigger volume will have a larger B value, and so therefore there would be a bigger deviation from the ideal gas law. Okay? So, one of the big things we've got to worry about is the volume of the individual gas particles. Okay? And we can think of, if they ask us, or if questions were asked about this, the bigger the gas particle is, the bigger the deviation will be. This tends to be a bit of a secondary effect as compared to the other big value or big concern we have with the ideal gas law, which is the attractive forces of the particles. We said originally that the gas particles have no attractive force. They do not interact with each
Particles
other.
continuously change direction and velocity as a result of
That the gas particles bounce off each other and don't interact. That there are no attractive forces between the gas particles or the walls of the container. But we know that that's not true. That the gas particles some of them are polar molecules, and those polar molecules would have some attractive forces, particularly as the gas molecules got close to each other. They would align, and there would be an attraction for positive and negative electrostatic Coulombic attraction that we should probably take into account. Typically, the way that we do that is by thinking about how, if the gas particles tend to attract each other, they end up pulling the gas particles in towards the middle. If you envision a gas particle on the edge, right by the surface of the container, there are a lot of gas particles towards the middle of the container and none at the edge. So the ones towards the middle tend to pull the ones towards the edge inwards. That has the effect of artificially reducing the pressure that we measure. Okay, so when you stick a pressure gauge on there, the gas particles don't hit the pressure gauge as much as the ideal gas law would envision. Okay, so you have to correct the ideal gas law for that change. Now, the correction factor for this depends on the density of gas particles, how many gas particles there are in a given volume, and it depends on how strong are the attractive forces. So the corrective factor here depends on the particle density, and it turns out to be a square factor, and A. This A factor measures the strength of the attractive forces between the particles. In general, the strength of the attractive forces is going to correlate pretty strongly to the polarity. High polarity molecules will tend to have stronger attractive forces, although nonpolar molecules, if they're large, can have attractive forces driven by London dispersion forces, a type of temporary polarity that we'll talk about when we come back from winter break. In essence, we have two corrective factors to the ideal gas law that we need to be aware of situations where these factors might take on greater importance, or they might be more important for correcting and calculating what's going on in the gas. So we can put these into the ideal gas law. We've talked, sort of about that, and we can see that what I do is instead of simply putting pressure in the ideal gas law, I have the pressure plus some corrective factor. And instead of just the volume of the container, I have the volume of the container with some corrective factor. Okay? Question?
How does the attractive force affect the pressure?
By keeping the particles from hitting the container walls.
Oh.
That's essentially what happens. What we also need to think about is under what conditions will this deviation from ideal behavior be more important, okay? And since it depends on sort of the volume of the container and the sort of particle density, situations where we have a high particle density and a small volume tend to be ones where we have to be concerned about these sorts of things. So that tends to happen when we have very high pressures, when we're in high pressure situations, and low temperature. Okay, if the temperature goes down, these values, the volume will go down. Okay, if we increase the pressure, the volume will go down, and then we'll have more particles in a given space. More particles in a given space mean that the attractive forces can come into play more often, and that the volume of the container is going to be smaller, and therefore the volume that the particles take up will be a more important factor, a higher percentage of the total volume. So the ideal gas law runs into most trouble when we're talking about situations of high pressure and low temperature. Under high pressure, low temperature conditions, the ideal gas law is less likely to match reality. Okay? These corrective factors can get us closer to reality under those conditions, but they're still not going to give us a complete picture of the true complexities of trying to model a gas under those conditions. But they do allow for a wider range of pressure, volume, temperature conditions to be modeled with greater precision, greater fidelity to the real world than we would see if we just tried to use the ideal gas. Most of the stuff that we're going to be asked about, I believe, is going to have to do with comparing different molecules and looking at how they deviate from ideal behavior. Most of the questions we tend to see are, which of these molecules deviates the most from ideal behavior? Or under what conditions would this molecule deviate from ideal behavior? Okay, those tend to be the kinds of questions we're likely to see. They used to have this equation on the AP test. They took it off. So they're not going to ask you to do calculations with this equation anymore. But they are still going to ask about qualitative things. And in particular, the new guiding document for the AP test talks about the analysis of graphs as a way to figure out deviation from ideal behavior. So let's take a second, look at how some real gases might compare to ideal gases. Okay? So here is a graph of pressure versus temperature. And here's what you see if the ideal gas law, if you have a pressure temperature relationship in a fixed volume with a fixed number of moles, say 1 mole and 22.4 liters of volume or whatever. This is the line that you get. You get a straight line. It's a linear relationship between temperature and pressure. Increasing temperature causes an increase in pressure. Okay? So this represents the ideal gas. A gas that follows ideal behavior will match this line. Okay? Probably one of the gases that's going to be closest to this is going to be helium. Okay? Helium is very small, so the actual particle size is a simply 2-proton, 2-electron atom. And because it's so small, it's nonpolar. It has very low. Wait, hold on. This is not right. So we're in fourth period.
Oh,
Yeah. So you go to
the wrong
page
one.
214.
Sorry.
So helium has very weak attractive forces. It's nonpolar for a variety of reasons. It doesn't form those London dispersion forces very well. We'll talk about that a little bit later when we get back. But if I graph helium's pressure-volume relationship, taking into account the corrections for what's known as the van der Waals equation that we were just talking about, they are basically the exact same. Helium will behave like an ideal gas. And in fact, helium remains a gas way down here. It actually only condenses close to absolute zero, tens of degrees Kelvin. So this is helium represents essentially our ideal gas. It will behave like an ideal gas under almost every condition that you can imagine. Now, another molecule, something like water, is still relatively small. A water molecule is a small molecule. It's 1 oxygen atom, 2 hydrogens. The hydrogens are tightly bonded onto the oxygen. It's a really small molecule. So volume effects tend not to be that important for water. But in terms of the strength of attractive forces, what do we know about water? It's a very high polar molecule, very high polarity, a large dipole moment. There will be a lot of attractive forces. Okay? That's the reason why water stays a liquid at room temperature. When other gases, things like carbon dioxide or nitrogen gas or oxygen gas or lots of other gases that we can talk about, which are significantly larger molecules but have weaker attractive forces, will function as gases. They'll behave as gases. Now, if we look at water as a vapor, water in the gas phase, if we graph this relationship, taking into account the strength of the attractive forces and the size of the water molecules, although that's not a big factor, we get a graph that looks more like this one. There was a little bit of lag on my button press. I'm not sure why. So the green line here represents water. Okay, this represents the pressure-temperature relationship in water. what we can see is that in this system, the water line is significantly lower than the line for our ideal gas, helium. Okay? The bigger the deviation, the greater the attractive forces and or size of the volume of the molecule must be. When we have larger attractive forces, we get this line. This is the relationship. You see that it changes not necessarily the slope of the line, but its position on the y-axis. Okay, the relationship between pressure and temperature still remains roughly linear over this range, although it tends to get a little funky down here. It still has that linear relationship, but it is shifted due to the attractive forces in the water molecule. Okay, greater attractive forces, greater shift in these lines. Okay? So, that's pretty much what I think you need to know about real gases. Real gases are gases that do not follow the ideal gas law. Most gases follow the ideal gas law under room temperature, atmospheric pressure conditions, although you would have to, read the problem and make sure that they tell you that it's an ideal gas law, or tell you, more importantly, when it's not. Questions that involve talking about under what conditions a gas will no longer follow the ideal gas law are going to be questions that involve talking about high pressure situations and low temperature. At high pressures, low temperatures, then the gas particles tend to be tightly packed together, which gives greater chance for attractive forces to come into play, and that the volume of the particles tends to be a larger fraction of the volume that the gases occupy. Greater attractive forces in a molecule, generally higher polarity, or as we'll learn later, greater nonpolar attractive forces, because those do exist, London dispersion forces, will cause gases or molecules to deviate from ideal behavior. Okay? All right. So that's about it. We are, in essence, done with new material. That's all the stuff we need to know about gases.